All right, so we're going to look at the last part of chapter 10. This will wrap up this chapter for us, and this should not take very long, but I want you to ask to pause the video if you need to catch up or write something down, or if we need to back up because you missed something. So take a second and get out your own notebook paper, your calculator, and you're going to need that during today's lecture. So we're going to start with empirical formulas. We've talked about molecular formulas. We'll talk about that again at the end of the chapter, but let's discuss empirical formulas and how you can calculate the empirical formula of a compound. So the empirical formula just gives you basically a ratio of the elements that are in the compound. This does not give you the number of atoms, which makes it a little bit confusing, actually. So the lowest whole number ratio is probably the most important part of that statement right there. So empirical formula, if you're taking notes, which you should be, don't copy down the whole entire slide. I'll show you what to copy. So just write for the definition of empirical formula: lowest whole number ratio in a compound. Now, sometimes the empirical formula and the molecular formula may be exactly the same thing. And we'll see an example of that in just a few minutes. Sometimes it won't be exactly the same thing. When we look at hydrogen peroxide is H2O2. That tells us that there are two H's and two O's, and if I were going to draw hydrogen peroxide, it would have two O's connected together, like this, a H right there, and an H right there. There are two O's and there are two H's. Okay, but the empirical formula is the ratio. So if the ratio is 2 to 2, which is what's right here, 2 to 2, then that is going to reduce 1 to 1. So then the empirical formula would be HO. For carbon dioxide, and here's an example where they're exactly the same. CO2. You have one carbon for every two oxygens. That's a 1 to 2 ratio. You cannot get any smaller than that. So the empirical formula and the molecular formula is exactly the same. So if you're going to write down an example where they are the same, that would be it. These are two compounds that have the same empirical formula, but they have different molecular formulas. And we're going to see later that that's based on weight. So they have the same exact empirical formula of CH, 1 to 1 ratio of CH, but different molecular formulas. So watch. If we look at this one right here. Let me turn on my highlighter. This one right here. C2H2. That's a 2 to 2, or reduces to 1 to 1 ratio. And then if we look at C8H8, which I think might be covered up by my little logo there. C8H8 is 8 to 8, but it also reduces down to 1 to 1. So you can see why there are different empirical formulas. But if I were to draw out what that actual compound looked like, there would be 8 carbons for styrene and just 2 for the other. So the percent composition, which you guys have already done that. The percent composition of a compound can be used to calculate the empirical formula. So let's take a look. It tells you the ratio of the masses. And so you can use those masses. You can use those masses to convert to the ratio of moles. based on molar mass of each element. Again, you can always ask to pause if you need to jot down some stuff, but this is percent composition used to calculate the empirical formula, and you'll be using molar mass of each element. Okay, so let's go through an example. There's a compound that's been analyzed that has 25.9% nitrogen, 74.1% oxygen, and it's asking you to find the empirical formula. Always write down what you know, and in this case, it's just percentages. Notice in the previous couple of slides, it says you need to know the molar mass. So let's look at this calculation. This was the percent given, okay? 25.9% nitrogen. Nitrogen is 14 grams per mole. That's its atomic mass unit. Notice that 14 goes on the bottom so that it can cancel out. Grams and grams, that leaves you with moles. So you're calculating 1.85 moles of nitrogen. Okay, do the same thing for oxygen. 74.1% divided by 16 grams per mole gives you 4.63 moles of oxygen. Notice this box right here. Percent means parts per 100. So if you had 100 grams of that compound, then it would contain 25.9 grams of nitrogen and 74.1 grams of oxygen. That is why you can use the gram symbol here, and that it cancels out with grams when you're doing atomic masses. So the mole ratio then of nitrogen to oxygen is real weird looking. It's 1.85 to 4.63. So what we need to do is to get that to a whole number. If you want to divide by the lowest, by the lowest molarity, 1.85, divide both of those by 1.85, you get 1 to 2.5. Well, you still can't have 2.5 atoms. Okay? So the next thing you want to do, if you have a decimal, is multiply each part of the ratio by the smallest whole number that will convert to whole numbers. So really what you're going to have to do is just say times 2, times 3, times 4, times 5. In this case, you can multiply times 2 and get whole numbers, because 1 times 2 is 2, 2.5 times 2 is 5. So your empirical formula now is N2O5. So when the subscripts are whole numbers, you're done. And that would be the empirical formula. Take notes on 2 more examples. Let's see. All right, what if you were given 94.1% oxygen and 5.9% hydrogen? This is when you need to get out your calculator, by the way. Okay, so the first thing that we need to do is find the atomic mass units for oxygen and for hydrogen. I think by now you probably know these, but oxygen's going to be 16 grams per mole. And we always want to use 2 decimal places, except oxygen is 15.999. So it's one of those that we can round all the way up. Hydrogen, 1.01 grams per mole. So let's look at oxygen first. It's 94.1 divided by 16 grams for every 1 mole. And if you guys will multiply that out, 94.1 divided by 16 should give you 5.9 moles of oxygen. If we look at hydrogen, 5.9 grams, 1.01 grams for every 1 mole equals, and if you'll calculate that out, you're going to get something very similar actually. 1.84 is what I got, moles of hydrogen. Now if you divide both of those by the smallest molarity, which is 5.84, you get approximately 1:1. So a 1:1 ratio is going to give us an empirical formula of OH. And it doesn't matter which way you write it. Okay, let's do one more example. What if you have 67.6% of mercury? That's a little different. 10.8% sulfur. 21.6% oxygen. Okay, let's start with mercury. Mercury is very heavy, okay, so it's 67.6 divided by, its molecular weight is 200.6-ish. I don't have the periodic table that's on the wall in front of me. So if there's another decimal place, you guys can use it. Per mole equals, and if you divide that out, you should get about 0.33. Sulfur. Sulfur is 10.8 divided by 32.06 grams for every 1 mole. Again, if you divide that out, you get about 0.33 moles. Oxygen. 21.6 divided by 16 grams for every 1 mole equals approximately 1.35 moles. So I'm going to have to use a different page. You guys keep taking notes. So for mercury, we calculated 0.33 moles. For sulfur, we calculated 0.33 moles. For oxygen, 1.35 moles. And so what you're going to do is you're going to find the smallest, divide by that number, and what do you get when you divide 1.35 divided by 0.33? You get 4. So our molecular formula, empirical formula. Empirical formula is Hg. 1 is understood, so we don't write that. S, again understood. O, 4. This is your empirical formula. Okay. Now let's look at molecular formulas. How do they compare? If you look at this chart right here, you can see that this CH, C2H2, C6H6, they all are going to have the same empirical formula because this one is a 2:2. I don't think I can get my stylus to write that small. That's a 2:2 ratio, which is going to reduce to this CH. This is a 6:6 ratio, which is also going to reduce to that. So all 3 of these would have the same empirical formula, but 3 different molecular formulas. Okay, and same for this. That's going to all reduce to the same empirical formula. Okay, the molecular formula of the compound can be the same or it can be different, but we can determine if it's going to be different if we are given a little bit more information. You have to know, let me highlight that for you, you have to know the compound's molar mass to be able to decide if it's going to be the same or different. So if you know the molar mass, you can calculate a ratio number. It's going to be a whole number, and determine if it's going to be a different molecular formula. So here are the steps. Write these down, okay? You can calculate the empirical formula, mass. So here's a new word, empirical formula mass, EFM. You do it the exact same way as the molar mass, all right? So whatever you're given, you use the AMUs on the periodic table. So step number 1, molar mass. Step number 2, we're going to divide. And then step number 3, we're going to distribute. Let's do an example. Okay. Calculate the molecular formula of a compound if the molar mass given is 60 grams per mole and the empirical formula is given as CH4N. Okay, so the first thing that we have to do is calculate the empirical formula mass. This is just telling you what you know and what you don't know. So calculate the empirical formula mass. First step. You are going to add 1 carbon plus 4 hydrogens plus 1 nitrogen. And that's going to give you 30 grams per mole. The next step we said was going to be divide. You're going to divide that empirical formula mass that we just calculated. You're going to divide that into the molar mass that was given in the problem. When you do that, you're getting this number 2 right here. Then you're going to distribute. I said distribute. But distribute to the empirical formula. So you're literally using like the distributive property. Here is your number that you just calculated. Here is the empirical formula that you were given. So give carbon a 2. Multiply that 4 in the hydrogen by 2 to get H8. And then give nitrogen 2. So here is your molecular formula. The molecular formula then has the molar mass of the compound that you were given in the very beginning. If you need to double check it, you can add it up. Let's do another example just to make sure we know what's going on. Find the molecular formula of ethylene glycol, which is used as antifreeze. The molar mass given to you, 62 grams per mole. Write that down. 62 grams per mole. And the empirical formula, CH3O. Okay, I'm going to have to go back so I can memorize this. 62, and then CH3O. 62 grams per mole, CH3O. Okay, so find empirical formula mass. That should be something like 12.01, 3.03, because we have 3 of those, and 16. So if you add those up, 11, carrier 1, we have a 31.04. Divide that number into that one. Let me change colors. So we have 62 divided by 31. I'm pretty sure you can probably do that in your head. That's going to be a 2. Distribute that here. So that you're going to give a 2 to carbon. Multiply the 3 by a 2. And then give 2 to oxygen. So that your new formula, C2H6O2. That's our molecular formula. This tells us exactly how many carbons, exactly how many hydrogens, exactly how many oxygens. I think that might be it. All right, you probably have got some problems to work on, so get those done, and I'll see you soon.